Welcome to VINDAL'S Concepts, and remember to subscribe, like, and share. It's very important. It's going to help us to go viral. And remember, we treated linear expansivity 1, and that is question 1, where we did a little, very short introduction. We're going to continue with what we did in the first one. But this time, like I said in the first lesson, linear expansivity is given with this symbol, alpha, which is something as L2 minus L1 all over L1 times theta 2 minus theta 1. Sometimes you can also say that this is change in length all over original length times change in temperature. It depends on the question, and both this and this, they are the same thing. Now the question is, what do you use as the LCM of linear expansivity? The LCM is, if you look at this very well, length is in meter, right? All over this length is also in meter, and this temperature is going to be measured in Kelvin, and this is K. So this cancels this. I have 1 over K. Therefore, SI unit of linear expansivity is given as 1 over K, or K per 1, or that is per K, sometimes per K, or K raised to minus 1. And that is why we say that linear expansivity of brass is 0.000018 per Kelvin. Now, looking at the question we have today, we say that when a brass of length 100 cm at 50 degrees Celsius is heated, its change, is heated, its length changes to 100.054 cm at dash. There must be a temperature when the length has increased to this new length, where the linear expansivity is given as this. So I'm going to continue from what I was saying. If you look at this very well, you realize that linear expansivity of brass is given as 0.12348 per Kelvin, and then that linear expansivity of brass is given as L2 minus L1 all over L1 times change. I'm not using change, I'm going to say theta 2 minus theta 1. So this is what I'm going to use based on the kind of question that I have. Now, if you look at this also, the linear expansivity is there. L2 is, this is the L2 because this is an increment in length. Then L1 is 100, which I'm going to put there. The theta 2 is what I'm looking for. Theta 1 is 50 cm. So I'm going to slot in these values to see what we are going to see as our new temperature. Now let's go. So I'm going to convert this to standard form, probably to be easier for me. Okay, let me use it normal. 0.12348 is equal to 100.54 minus 100 all over 100 times theta 2 minus 50, all right? Now, somebody might have asked, why can't I change this to Kelvin? It's not really necessary. Let's use Celsius to continue solving. So we now have 0.12348 is equal to, this is going to be this is 0.054. So this is going to be 0.054 all over 100 theta minus, all right, because I said this times this is theta 2, so I'm calling theta 2, and this times 50 is going to be this 50,000, or sorry, 5,000. So I'm going to clear the fraction. So I'm going to have 0.00018 times 100 theta 2 minus 0.00018 times 5,000 is equal to 0.054. All right. So 0. In this case, this 2 zeros and this is going to move 1, 2. So this is 0.0018 theta 2 minus, and this times 5,000 is going to be 0.09 is equal to 0.054. All right. So this is going to add plus 0.054, and that is having I have theta 2 is equal to, if I carry this to this and add, so I have 0.144 divided by 0.0018, which is equal to divided by 0.0018. And this is equal to 80 degrees Celsius. That is the temperature when the length has increased to this. Thank you very much. Please don't forget to share, like, and comment. This is VINDAL'S concept.